this is a table with some standard electrode potentials, reduction potentials for several elements in aqueous solution at 25 degrees, 298 kelvins. All the electrode potentials are measured with respect to the hydrogen ion, which is given the value 0 and at all temperatures, and all the other potentials are measured against that hydrogen ion electrode. And the value tells us if that particular process is going to be spontaneous or not. The value of the electrode potential needs to be a positive number. They're all given in reduction form. All the tables are electrode potentials of reduction reactions, but just by changing the sign, you have the value of what would be the oxidation reduction. So for example, in this first one with cadmium, if instead of writing cadmium with cadmium 2, you write cadmium to produce cadmium ions and liberate electrons, the value for this electrode potential would be the same numerical value as the reduction one, but a different sign. So with one value, with one table, you can actually have both electrode potentials, the one for the reduction reaction directly and the one for the oxidation reaction, just changing the value. So how do we use this to predict the spontaneity of a particular redox pair, of a particular oxidation and reduction half cells? So the electrode potential of a cell of a particular redox pair, a reduction and an oxidation reactions, and whether it would be spontaneous or not, would it be if we would be able to construct a galvanic cell using that particular redox pair is based on the electrode potential of the cell they make. And that is the electrode potential from the tables of the reaction involved in the reduction, and the electrode potential from the tabulated data of the reaction involved in the oxidation process, and with a minus here. And if this electrode potential is a positive number, then we know that the reaction is going to be spontaneous, and that is potentially a viable galvanic cell. That particular redox pair will produce an a current. So for example, if we look at this particular reaction, silver metal with in acidic medium with hydrogen ions to produce silver ions and hydrogen, would this overall reaction produce electricity? Would we be able to construct a galvanic cell? And when you're looking at these structures, when you're looking at electrochemistry and standard electrode potentials, you do not need to balance the equation, which feels quite counterintuitive. Very rarely a chemistry lecturer will tell you do not balance the equation. In this case, it's because the number of electrons exchanged will be the same, and the voltage of that reaction will be the same. The concentration, the number of ions involved, etc., will affect how long that cell will run. So higher concentration, lower concentration will affect the amount of time that reaction takes place, that galvanic cell runs, but the voltage will not be affected. So just use the half reactions as they are, without trying to without balancing them. The balancing will come at a later stage when we are using the Nernst equation, and that's when, yes, we do need to be careful to know what's the number of electrons exchanged and the different coefficients of all the players. Because we are going to be using an equilibrium constant. At the moment, to answer this question, I'm going to ask you to stop the video, to go back to the table of electrode potential, or the one you have on Blackboard, and look whether this reaction would give you an electrode potential for that particular cell, which is a positive number. Stop the video now, please. So how would I go about answering this exercise? How would I be able to predict whether this particular redox pair could be used to construct a galvanic cell? Well, first I need to identify the oxidation and the reduction process. From one hand, I've got the silver that produces silver ions, and on the other hand, I have the hydrogen and liberates one electron. On the other one, I have the hydrogen, which produces hydrogen ions, which produces hydrogen. And again, I don't bother about balancing the equation, although I might need to balance it and to go and find I don't bother balancing the overall equation. What I do need to balance is the individual equations to be able to find them on the tables. So I go to the table and I look and I try to find those two semi-reactions. So the silver one, I can find it here in a different, it's the other way around. This is giving us a reduction process and as a reduction reaction, but the value is there. And I can also find the one for hydrogen, which is here, and it is 0. So on one hand, I've got 0 as the electropotential for the reduction process, and on the other hand, I have 0.80 as the electropotential for the oxidation process. So if I go back to my slide and I remember that the electropotential of the cell is the electropotential of the reduction process minus the electron potential of the oxidation process. So I've got the electropotential of the reduction process would be 0 because this is the reduction process. And the electropotential of the oxidation process, this one here, is 0.80. And I put minus 0.80 because it's going to change this is taking care to change the sign from the table in which is written as a reduction into the equation in which we are taking into account there is a oxidation process. This value, minus 0.80, is a negative number. So no, the answer is no. This cell, this electropotential is not positive. This overall reaction could not be used to construct a galvanic cell because this process is not spontaneous. The electropotential is a negative number.